Okay, so let's start. We proceed to regular lectures of Stephen, and the title is, you can read, it's slightly different than what is written in this program, but both themes are very
Okay, so I changed it because I think maybe this one is a little bit more radical, and so it might be a little bit more interesting. So it's actually about the whole idea of optimization actually being embedded in things like controllers. So that's the idea. And so there'll be almost no theory in this talk. But I think it's a very, very important phenomenon, an idea. So I'll start. I'll say a little. I'll say what is real-time embedded context optimization. We'll look at a bunch of examples. They're very simple, but just so you see what the idea is. Then I'll talk a little bit about parser solvers for convex optimization. You've already seen some of this, and if you use CBX, you know what these are. Although probably you don't know how it works. That's another talk, and it's actually very interesting. And then I'll talk about stuff probably none of you have seen, or very few. It's code generation for real-time embedded optimization. So that's so it's going to be a different style. Okay, so what is embedded optimization? Well, the idea is you're going to embed a solver in a real-time application. So, for example, in a controller, you might solve an optimization problem every single step. So you would solve an optimization problem every step. But it could be in signal processing, it could be in many applications. And of course, this is not a new idea by any means. It's used widely, and whole industries are run by it. So in process control, they use MPC, and they solve a big QP at every step. And they've been doing this for 15, 20 years now. So for 20 years now, industrial process plants solve a quadratic program every 15 minutes. Supply chain and revenue management are entirely run this way. So in supply chain, you solve a giant LP, maybe every few hours, every day. And from that, you determine what goods to move to what places, right? So what orders to make. Revenue management, that's a euphemism. Revenue management is not actually such a great thing. That's a method for a company to extract as much money as possible from you, right? So an airline will have a whole bunch of different seats, and then they'll reserve some that are very high priced, and then they wait until the last minute, and then they release some, and all this kind of stuff. It's actually probably not a good thing for the general public. It's very good for the companies. And trading, essentially all quantitative trading, all quantitative trading, except for fast trading, which is just straight fraud. But fast trading, other than fast trading, all quantitative hedge funds and things like trading is done using optimization, so embedded optimization. So all trades are determined by solving optimization problems. But everything here is on an hour or minute time scale. So that's the difference. Okay, so here's what's new. What's new is that you can actually carry out optimization at the millisecond and microsecond time scales. You don't even hear it. I mean, it's not something people even think about. So traditional problems, don't take this too seriously, right? Because it's just a picture. But the idea is that, normally people do talk about solving an optimization problem in a few seconds, it could be hours, and it could even go as long as days, right? So for example, if you're doing circuit synthesis, which is designing a circuit, it's completely typical for the circuits like the ones in my iPhone or this thing. Those can take 1 day up to 2 days, 2-3 days. And that's completely standard. That's what people do. Okay? So those problems, of course, involve millions or more variables. So this is the idea, and there's of course, you would love to look at problems. You'd like to be able to solve a problem with 1 million variable microseconds. This is kind of, you can actually do some quick estimates about how fast you can move data, and know that you can't do that. At least now, maybe in 15 years. So we're going to look at sub-second down to the microseconds, and we're going to look at what people in optimization consider to be small problems. Problems with a few thousand variables, a few hundred, even tens. Right? So this is this. And I should say why this is essentially unexplored. It's unexplored for several reasons. The first, I think, is almost a cultural one. That when people think about optimization, I think so far it has been conceptualized as something where there's a person in the loop, right? So if you're designing a controller, you design it and you look at it, you simulate it, and all that kind of stuff. And so if there's a person in the loop, it doesn't need to be faster than a few seconds. It has no meaning, right? Because a person's going to look at it, you're going to simulate things, you're going to look at some plots and things like that. And that's true for all sorts of problems. It's also true in finance, right? That if you're trying to figure out what trades to do, you solve an optimization problem in Excel or something, and if it takes 2 seconds, if it takes 10 seconds, it's fine, because you're going to look at it and then play with some things and do it again with a human in the loop. So if you have a human in the loop, there's no reason for a problem to solve a problem faster than a second. There's none. This doesn't make any sense. So I think that's why there's been essentially nothing here. Also, of course, if you work on numerical methods for optimization, the way you impress your colleagues is by solving problems that are gigantic. So that's what you do. We show up at the next conference and you say, we just solved a 10 million variable SOCP in 2 minutes. That's the kind of thing. You don't show up at a conference and say, what have you been doing? And you go, well, I just solved a problem with 37 variables. This is not going to impress anybody. Right? So, well, I mean, unless you say they did it in microseconds, but they don't even think about this, so they can't even process it. In fact, I gave this talk to a bunch of people in optimization, and it turned out most of them were in OR, and some of them were quite confused about what the difference between a millisecond and a microsecond was. So it was pretty weird. They knew it was something that was less than a second, they just weren't too sure what it was. Okay, so what are the applications? Well, I mean, abstractly, you do real-time resource allocation. And so this actually, this is a big thing. Even a single processor now, or you take a data center, or you take a multi-core computer, anything like that. There's all sorts of stuff happening. And there's resources like memory, bandwidth, all sorts of stuff. And you can easily imagine these things. In fact, it's being done now. People are doing resource allocations all using entirely ad hoc techniques, right? So it's the people who do systems, computer systems, who design these things. And they make the schedulers and things like that, and it's all ad hoc. Almost all ad hoc, right? So, but you can easily imagine doing this not ad hoc, right? So that would be one. In signal processing, here you might estimate a signal by solving an optimization problem over a sliding window, right? And then you can do things like this. Once you're committed to actually doing some serious numerical work, every sample or every 10 samples or whatever it is, you can do crazy stuff like this. You can replace standard least squares estimates with things like robust versions, and we're going to see examples of this. Right? So you could replace what was a least squares estimate, which would give you a Kalman filter. You can replace that with L1 or Huber. Right? Huber is a penalty function that's quadratic, and then it transitions to linear. Right? So it looks like for small things it's least squares, but then for large outliers it is L1, and it's incredibly robust to outliers. So in control, well, it's obvious. I mean, there are many applications. I mean, one is you can simply do closed loop control. So you do rolling horizon optimization, receding horizon optimization, MPC. It has many names, right? So you could do this. The other things, you can do things like real-time trajectory planning. So you can take something and you can say, please move it as soon as possible to another configuration, and in half a millisecond, you compute a minimum time trajectory to move something somewhere, right? So, I mean, you can just think of many examples of this. So, all of these things are done now, every single one. But they're done, it's on a long time scale, like minutes, right? Or if anything, seconds, but even that, it's not really done. So it's seconds, minutes, hours, this kind of thing. But the point is, they could be done on a millisecond or microsecond time scale. That's the, I think, and I think actually this is, this is unbelievably important for control. I think the implications of this are very profound. I mean, I know I've had to rethink myself. You know, the story always went in control like this. You have a person in control and you have a person in operations research. And the person in operations research, you know, they do the same thing, right? Both of them say, we get data, and then we use a computer to make some sophisticated, you know, decisions, and then we apply the decisions, and then we repeat this or something. And it's the same thing. But the person in control says, oh, no. The person in optimization says, oh, well, I solve an LP or a robust LP or something like this, right? And the person in control says, well, I understand all that, that's fine, but, you know, I control jet engines. I have to make a decision every 20 milliseconds or something like that. You know, or I'm doing navigation. I have only 1 millisecond to make a choice. So I can't solve, you know, one of your LPs or something like that. Anyway, I guess what I'm trying to say is that's wrong. It can be done. So I think it was true in the 60s that if you wanted to do control, yeah, you can pretty much multiply by a gain matrix, a state vector, right? Or update a Kalman filter. Things are different now. In a 50th of a second, that's 20 milliseconds. The amount of computation you can do now is stunning. And I think this has huge implications for control. Okay, so we're just going to look at examples. They're, of course, simplified, they're just for fun. So here's one. Let's do speed scheduling. So probably most of you know that all modern processors, including the ones in there, and every one, all of yours, including, by the way, all of your mobile devices, everything else, you can vary the speed on the processor, right? And you can vary it, you know, sometimes in discrete, but sometimes continuously. It's usually discrete things, but we'll consider it continuous. And you vary the speed. What happens is, and you can usually vary it in maybe 50 millisecond increments. I mean, usually it doesn't do it that fast, but it can. Okay, and the idea is, and is that you adjust your speed, and the speed says how fast you can carry out calculations, but it also affects the power dissipation in it. So this is the trade-off. And the energy consumed is a function of the speed. This thing is always convex, in fact, always. So, because the marginal cost, if you run at higher clock speeds, is higher, right? And in fact, actually, for most modern processors, this thing is very close to just a square, right? It's just a square. No, and it's not for a simple reason. It's like 20 different reasons put together, and somehow when you put it all together and you plot this energy versus speed for a modern processor, it looks like a square. So, anyway. Okay, so the idea now is you have a bunch of jobs, and each of these jobs has an availability time and a deadline. So the job, you can't start the job until it's available, and it has to finish by a deadline. And it has a total amount of work that you have to give to it, right? And so if I let capital S Ti, that's the effective processor speed allocated to job I in period T. So for example, if the processor is running at 2.2 gigahertz, I could say this job gets 200 megahertz, this gets 400 megahertz, and so on. Right? So that's you allocate that. Okay. Well, if you sum over the jobs, you get the total speed. That's little SD. And if you sum now, so the S is a matrix, right? And you have jobs and you have time. And if you sum across jobs, you get the speed of the processor. And if you sum across time in each row, but only in the place where it's you're allowed to process it, that has to exceed the total work in each job, right? Because this is, and this is just a simple model. This is what it might look like, right? Okay. So minimum energy processor speed scheduling is this. You choose the speeds and the allocations this is to get all the work done. This is to respect the minimum and maximum, and that's to minimize the energy, right? And that's a convex problem. And you can imagine all sorts of things here. You could have multiple processors, you could have thermal things and speed slew rates, and you can also imagine a case where you don't know the data, right? This is the data that tells you how much work you have to do, when it's available. So, and you can imagine that's stochastic, right? So that would be another one. Okay, so that's speed scheduling. And let's look at the example. And the example is just to show it does something, right? So it's just a made-up example for us to see. So here's the example. You have a range of speeds from 1 to 6 with a square cost. Actually, this is wider than most ones. I think this one ranges over a 1 to 3 period. The processor in there is an atom, and it runs over like about 1 to 3, not 1 to 6. But you know, these are actually the hilarious part is, although these are all made up, they're not that far from the real thing. These are not too bad. And we'll take the square as the energy cost. And here are the jobs. And the idea here is that the width shows you it's available here, and it finishes there. That's the deadline. And the area of it is the total amount of work to be done. So this job, for example, it's a simple one. You've got very loose timing requirements, very little work to be done. So this is about the easiest job. That would be a tough one. That's a job that has very tight timing. It's available only in, something like 13. Has to be done by whatever this is. I don't know what that is, 17. And it's a lot of work, right? So and besides, it's just all made up, right? Just so you can see, you have a bunch of different jobs. Some simple, some critical, and so on. Okay. So here are the optimal and the uniform schedule. Uniform schedule just says that each period you take all jobs that are active and you process all of them uniformly, and you get this, right? Something like that. And you can see what happens. In some periods, there's a lot of work to be done. In others, there's none, and in fact, no, we never really get down below the minimum. But you can see there's an amount like this. This is the optimal one. And the first thing you see, this makes perfect sense, is Jensen's inequality, right? It tells you that this is going to, because you take the area of these two things is identical, it's the total work. But Jensen's inequality tells you that this will do better, right? Because, and in fact, in other areas, like in electricity generation, when you remove like these big peaks and push them down, it's called peak shaving, and it makes, that's kind of a standard way to describe what optimizing powers and stuff will do. But it's Jensen's inequality. And you can, of course, look at this and you can make a big story about it, and you can say things like, here, this big job, you could say, look at this big job knew that on the last step there was not much to do, so it did about half of what it was supposed to do, or 50% less than what it was supposed to do, knowing that in the end it was going to have this big thing. You can say, I don't know, this one you can say, this job here, for some reason it knew that on the first step it should process, 5 times as much as for the other ones. Why? Because it knew this job was coming along. I mean, you could make up a story for all of this stuff. So all of this is just to show it does something. And although everything's totally made up, so it reduces the energy. Of course, the numbers you should completely ignore. They mean absolutely nothing. Except to say, this does something. By the way, not only does it does something that no human being can do. Right? I mean, everyone here knows, if you see this up here, this thing is strongly convex, you want to push these down. I mean, that's obvious, right? So you could write some kind of, and an undergraduate could easily write some kind of heuristic thing. It would do something, but it wouldn't do this. And it wouldn't scale. Okay. Next one. Let's do minimum time control. And you should, by the way, you should stop me and ask questions anytime. Okay, so we'll do minimum time control. So here's just a quick example. It's got, you have a rigid body, but modeled with 2 vibration modes, right? So it looks like this. There's a main force that moves the whole thing. That's this force, and then there's a tension that's much smaller applied in between 2 parts of it, and that's going to be for active vibration suppression, right? So this is actually a picture of it's a very good model of a sophisticated active positioning system, and these are used everywhere. They're used in disk drives constantly. All high-end disk drives are used for 2-stage control. This is exactly what they do, right? And a disk drive, it's exactly this, right? Because you're at one track and you have to seek another one, and that's actually the most critical parameter of the disk drive, is how fast you can seek. This is also true for critical manufacturing, like in integrated circuits. You have an XY cable that moves. It'll move centimeters, and then it'll stop with an accuracy that is deep sub-nanometer. Okay, so I mean, it's completely insane, right? The accuracy is so good that you can't even use things like a short int to describe the positions. Even a float is actually not going to work. And it's unbelievable what these things do. And of course, those are universally used. Okay, so this is the goal is to move this thing from one place to another as fast as possible. You have a big force you can apply to the left, and a small force you can apply here. Oh, and now's my time to say something, because I figure I get the two things. I'll show you some technical things. I'll also make some comments. So I'm going to make a comment now. So you could take this problem, and you could say, oh, I learned about this, you know, and you could take out and you could start working out Pontryagin maximum principle and all this stuff. Okay, so you could do this. Guess how far you would get? Absolutely nowhere. You could do one, that would be completely trivial. You could do two, but it would take you a couple of days. Okay? You could get it. You get an explicit form for the optimal minimum time control law. Three, I doubt you can do. And anyway, this is not interesting. What you really want to do is a system with something like 25 states, 10 inputs. Okay? Then we're, trying to work out, the Hamiltonian and the Pontryagin maximum principle is a complete joke. It is completely useless. It is interesting culturally. It is interesting historically. It's interesting to understand how you might do it if you could, but you can't. Okay? So I'm just saying this.
Yeah. But the question is
Finally
how
worked.
we implement Pontryagin maximum principle. We write it not theoretical, but in some numerical method. We can do it.
Well, then you can do it. Yeah, that's fine. Yeah, and in fact, you could do this one.
Okay. We can reduce
Put it this
to a
way.
linear program.
Okay. Yeah, this is exactly that, and that's the right way to do it. Okay, so okay. All right. So if you ignore the vibration modes, everybody knows how to move a mass from one place to another in minimum time. Is you apply a bang-bang control. You accelerate to half point, midpoint, reverse, and you brake. And you get this. But of course, this is vibration mode, so you get this kind of thing. Okay? So that's ignoring the vibration modes. But in fact, the problem is it's a linear program, or it's really a quasi-convex problem, but it involves linear programming, right? And it's extremely straightforward to do this. And it's a quasi-convex problem, and there's the solution. The blue shows you the solution, right? Here's the optimal tension, that little vibration suppression should do this, and that's the main force, right? And the point about this is this tiny little baby stupid example, but this solution is not remotely obvious. It's not remotely obvious, right? And I guess, to me, this tells you why we do what we do, right? Because, even for some simple 6-state system, take an airplane. We can synthesize inputs to airplanes and things like that, which no pilot could ever come close to achieving. Absolutely nothing, right? So when a modern airplane makes a turn, for example, it drops like 1 meter. It comes out down to a single knot. It is going the same speed, and no human pilot can do that. It's just impossible, right? So, and this is just out of the question. And if you think this is out of the question, try one with 10 masses and 20 vibration modes and 10 different inputs, right? This is so. By the way, I say this in a positive way. This is good news. This is what we do. Does real things, and it does stuff that no human being could ever do. So, and it's not remotely obvious. I mean, this does not look like that at all, at least to me. Okay, next one is from robotics. So here you have something you're going to grasp, and you're going to grab it with contact points, and then you're going to put a force on each of the contact points. And then what you're going to do is you want to resist an external force and torque. And it could be as simple as just the dead weight of the mass. So there's no torque and there's just a gravity force, right? But it could be that I could be moving this thing, and then of course I have to apply, I would work out along the trajectory what forces and torques I have to apply. And so what we'll do is this. There's the interesting thing here. Of course, this is a second order cone program. The tricky part is this, and that's very simple. That's as if I have a very simple model of friction is this, is I have an object, I apply a force, and if there's zero friction coefficient, the only force I can apply is down. Just nothing else. Just a normal force and into the object. Right? But if there's friction, I can actually move this force it can actually move over a cone, a Euclidean cone. And the angle of the cone depends on the friction coefficient. Right? So that's that. So you have, this is the friction coefficient, cone constraints. And then this says, this is expressed in the local coordinates, with the z-axis being into the object at the contact point. And then you have a bunch of orthogonal matrices that transform them to a global coordinate system. And this says that you mass the total force and you mass the total torque, right? And this says you can take many different objectives, but this is minimize the maximum force applied to the object. Okay, so that's an SOCP. So here's an example, just to see it does something. There's the contact points are here, 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 and here, and this is just the dead weight of the mass. That's the CG, and that's the weight. And so, not surprisingly, you don't push if you're holding it up against gravity. You don't push from the top, but you apply these forces here, right? And notice that this one is right on the friction boundary, and so is this one, and this one is not on the friction boundary. Here's just a force this direction. And you can sort of see what's happening. And now this one's on the friction boundary, this one is not, this one is. Here is counteracting, applying a force that goes, counteracting a force that goes this way and a torque that way, and you see the various things going on. Okay, so this is just to say, here's one where you have a strong torque this way, and so to counteract that, all of the forces are pushing, are at the edge of their friction cone, not this one, and they're applying a counter torque. So, I mean, nothing is counterintuitive about this, but at the same time, it would be a real pain for a human being to work to figure out what these are doing, right? And this is in 2D, and of course, you'd really do this in 3D, not 2D. So, okay. So how fast can you solve a problem like that? Well, let's see. So here's an example. This is actually across the street from me. There's actually an actual robot, and that has 5 fingers. And so you end up with what in optimization would be considered a tiny problem, right? A problem with 15 variables, 6 equations, a bunch of second order codes. And if you run this through, let's say CVX, it takes 100 milliseconds to solve. And in fact, most of that is not solve time, obviously. Most of that's parsing time and other stuff. And who cares? 100 milliseconds is fast enough for a human being to look at the forces and make those. It probably takes more time than that to render those plots, right? Than to solve it, certainly than to solve the SOCP. Okay, so, but if you write custom code for that, you can solve that in 50 microseconds. In fact, that's out of date. So the current time for this is about 10 microseconds. Okay, so 10, that's fast. So people don't usually talk about optimization and microseconds in the same, if you were to look at a bag of words model or look across Google or something like that, you're not going to find too many documents that include microseconds and second order cone programs. Right? So, and I'll get into lots of detail about how this is done. Now, by the way, this changes everything, right? This says, this is one thing. This says you can that means that actually optimal force stuff can be embedded in real-time control. I mean, even at 50 microseconds, that's 20 kilohertz, right? So that means you can actually do this in real time. You can just embed it. Okay. Another example is from signal processing, which is robust Kalman filtering. And this is actually a good one because it connects to traditional signal processing. And it's actually a good example of how I think in a lot of cases we should go back, look at the traditional methods and ideas, and then go back and reinterpret them or get new versions of them that work in this new regime where you're willing to solve an optimization problem fast, right? So here it is. So we do robust Kalman filtering. You have a linear dynamical system driven by noise, and so this is completely conventional here. That's just some Gaussian thing. We could just as well have put something non-Gaussian here. But the measured noise looks like this. It's the usual linear measurement plus the usual Gaussian measurement noise plus another noise, and the only thing you know about it is it's sparse. And so it represents outliers, just failures, intentional jamming or something like that. It could be anything you like, right? So just it's sparse. Oh, and I should say something about this. There's different regimes about for the size of ZT, and we should discuss them. If you have a sparse, if your sensor measurements are, let's say, on the order of between plus and minus 1, and all of a sudden you get a sensor measurement that's 10 to the 6th, you know it's wrong, right? So you just ignore it. So it's not this is not an issue. Anybody could write a simple thing that would remove, sensor measurements that were wrong, because they were huge. Now, on the other hand, if this thing had a variance of like 1, and ZT was less than 1, or 1, it wouldn't hurt anybody, right? It could just as well it could have been the Gaussian noise, and the standard filtering will work perfectly. Everybody see what I'm saying? So if the sparse noise is small, it doesn't hurt. If the sparse noise is huge, it's completely obvious, and anybody could remove it. So the trick here is the following, is to be able to handle sparse noises or outliers that are actually consistent with the typical sizes of inputs you see. These are the ones that are hard to do. Everybody see what I'm saying here? So this is a regime. That's the one that's hard to take care of. Okay. So how do you do this? Well, there's a steady state Kalman filter. It looks like this. That's without this, it's just a steady state Kalman filter. You do a dynamics update, and then you do a measurement update. Okay? And actually, the interesting thing is these are the formulas you know. And my claim is we have to go back and remind ourselves, in fact, where these things came from. Then we think that this is like an estimator of Kalman gain or something, and that's an innovation or a prediction error or something, right? And so, but in fact, this formula comes from solving an optimization problem. It's a quadratic optimization problem, so it has an analytical solution. Okay? So, okay. So what we're going to do is this. The first thing to do is to write the Kalman filter as something like this. It actually says to minimize, and in fact it has beautiful interpretation. That's the negative log likelihood function for the noise that you're estimating occurred. That's the prior, and this tells you how far you are away from it. And then that's an equality constraint. But this here is a linear, it's a quadratic problem with linear equations. We can solve it analytically, and of course the solution is exactly this, right? It's an analytical solution, and it looks like that. And we normally just write it this way. And when you implement it, like when you go in and you look at the C in the real-time code, it looks like this, right? So, but in fact, probably it's good practice when you write this to put a little comment at the end of the code that says, we are solving this. Okay? So what we'll do is this. And this is completely standard now in robust estimation and things like that. What we'll do is to handle this sparse thing, we simply add a one norm and a parameter lambda. Okay? And I'll talk about that tomorrow. So you solve this. Now when you look at this, it's still a convex problem. In fact, it reduces to a QP. But it no longer has an analytical solution, right? Well, it does, but it's stupid. There's a piecewise linear solution, right? Because it doesn't matter. But it doesn't have a simple analytical solution, this thing, right? So, okay. So we're going to solve that. First, we're going to do an example. And the example has a problem with 50 states, which is big, and 15 measurements. And then with probably 5%, the measuring components are replaced with just a noise. And by the way, what this does is the worst thing possible It produces an output, a measurement, which is plausible but completely wrong, right? These are the ones, right, because otherwise, if it was huge, anybody could detect it. If it was small, it wouldn't have any effect. This is the worst possible thing you could have. Okay, and since it's 5% and there's 15 measurements, it says that basically almost every sample, there's one of your measurements is wrong. It's actually worse than that. It's wrong but plausible, right? So almost every sample there's a measurement that's just wrong. So that's the idea. Okay, so here's how well it works. This is the norm of the estimation error. The red shows what happens if you just run a Kalman filter. And it makes perfect sense. You see these huge jumps. And the huge jumps up are because every time there's a wrong measurement, the Kalman filter believes it's correct and does something. And you can even see, like, for example, right here, there was a sequence of not lack of errors, because there's an error almost every step. What there was is they were benign errors, and they didn't hurt the Kalman filter, and then all of a sudden there'll be a terrible error and drive the state estimation down. Okay, this gray one at the bottom, I don't know if you can see it. That's if you had signed information as to which, if along with every measurement, you were told exactly which one was wrong. If you were told that, then of course you could run a Kalman filter as well. It's a time-varying Kalman filter, but you could do it. And you would get this. So that's a lower bound on what anybody could possibly do in this problem, right? That would be, you have secret knowledge as to which measurements are correct and which are not. By the way, it's not that easy to get the secret knowledge because, remember, the measurements are plausible, right? That they're in the same range of size, everything, as the other one. And the blue shows what the robust Kalman filter does, right? So, and the point is, it's like all the other examples. The only thing you're supposed to take away from this is, this does something. It does something that's actually very impressive. And it's done in a principled way. People, anyone who implements a real Kalman filter on a real system has all sorts of crap around it. It looks for the innovation. If it's too big, it rejects it. They have all sorts of things that remove measurements and outliers. This is just done in a completely principled way. Okay? Now, the big difference is, of course, you have to solve a quadratic program every step. So here, you have to solve a quadratic program with about 100 variables and various things. And in this case, automatically generated code, that's actually out of date. It doesn't matter. So if you run this in SDB, if you run it in CVX, you get 120 milliseconds. That's per step, right? So if you're running it 5, it's already fine, just in CVX. Just run it. But if you want to run faster, it's not going to work. So automatically generated code for this solves at 120 microseconds. This is actually down, I think, to about 40 right now. 40 microseconds right now. That means you can run this at 25 kilohertz. Right? So this is not on exotic hardware, anything like that. I mean, you put this on GPUs, you could probably do a lot faster than that. Right? So this is. So I think all I'm arguing here is that I think we're on the edge of a new regime. And the new regime is if you do real-time signal processing or control. Now, of course, if you do stuff at the gigabit rate, forget it. None of this applies. But a lot of other rates that people are talking about, if someone measures sample times in hertz, or even kilohertz, that's within striking distance of solving convex optimization problems every single time. And this hugely enriches what we can do to signals, what we can actually do if you allow yourself the idea of solving a convex optimization problem every step. Okay, we do one more. The next one is control, and it's this. We have a convolution system here with a saturation, and what we're going to do is we're going to make an equalizer here. What it's supposed to do is it's supposed to get rid of the effects of the saturation. Of course, it cannot completely. That's ridiculous, right? Because your input is limited. But the idea is that in an input that would overdrive this a little bit, maybe we can compensate for it, apply a different input signal to here, to this thing that would cause the Y to look very much like it would have looked if the saturation weren't present. Okay, so this is the idea. Okay. So this is what we're going to do. This is the reference system. So I want my input to look like H convolved with U. That's this signal here. And to do that, I'm going to do something in this box. I'll generate a signal that has to be between -1 and 1 or something. I will put it into this thing, and that'll cause an output, and I'll judge myself by this error. Okay? And so, for example, for no better reason, we'll just minimize the mean square error E, right? And what I'm going to do is I'm going to give this equalizer the ability to look ahead T samples, right? So that's the idea. Either look ahead T samples or have a delay of T samples, however you want to say it. So that's the. Everybody understand what it's going to do? So the way this works is the true system looks like that. It's got the saturation. The reference system looks like that. And then, well, our error is the difference between the true system output and the reference system output. And we would like this to be small. And so the state error just propagates according to a linear equation. And so we're going to use MPC. And all we're going to do is choose our input, subject to the constraints here, to minimize this cost function. I'll look forward T steps and minimize this. And that's a final cost. It could be the output parameter or something like that. That would be the case if you ignored the input saturation past there and did full least squares, right? That would extend that to infinity. Okay. All right. So let's look at an example. It's a problem. It's got state dimension 3, and the impulse response decays in around 35 samples. We'll look ahead 15 samples, so we're not looking ahead. We're looking ahead only at half of sort of the time response of the whole system. And then the input U is going to be random, and it saturates about 20% of the time, right? So if it's saturated 2% of the time, this would be easy. If it saturates 100% of the time, you would do badly because you can't compensate for that, right? So here's what happens. So you can't see it because it's covered, but there's a dashed black signal, and that's the desired. That's the reference output. The equalized one is the blue, and it's right on top of it. And the red is what happens if you have no compensation. Okay? And it's actually quite interesting what it does. Well, here are the errors. And so you can see, so the point of this is just to say, whatever this is doing, it's doing something and it's good. Right? It's better than you could possibly do. This is if you do nothing. That's the error you get. And if you put this nonlinear compensating equalizer in, you get an error that's like way small. Okay? And then if you want to see what it does, you can actually understand it. It's right there. And so what this shows is the input. So what it is the red is the input that's the input that came along. And you can see it's got these violations that go way over the limit. And you can see how the way it's compensated is this. The real input signal is not allowed to go outside ±1. But what it can do is it goes up early and holds it, so it makes it fatter. It simulates the effect of a large input signal by making it fatter and large. Everybody see this? I mean, this is like all of these things, right? After you see what it does, you can make up a story after the fact, right? I mean, at some point, probably the right thing to do is just stop making up the stories and just say, oh, it's optimization, it's doing the right thing. But anyway, so my claim here is this is not obvious exactly how to do this. And you can see it. You can see everywhere it's doing the right thing. Like here, for example, to simulate the effect of a single peak that exceeds the thing, you go down to -1 and you hold it for many samples. Everybody got this? So, okay. How long does it take this one is way off. I'll take the numbers now. This is a problem with 100 variables and various other things. It takes about 1/3 of a second now. And this one is now clocking in around 80 microseconds. Okay? So, it's not fast enough for audio. It's fast enough for low frequency audio. But it is fast enough for plenty of other stuff. Okay? So even this is kind of interesting, right? Because it says that if this is a process that has like a 15-minute time scale, you can actually essentially undo to a great extent the effect of saturation. Okay. One more. It's related to what I showed you last time. It says you have a linear dynamical system, and we're going to do linear quadratic stochastic control, but we have a constraint set, and we're going to pick this policy to minimize this average cost. Okay, and I talked about this yesterday about the idea of an ADP. This is the Bellman equation. I think we talked about that yesterday, so I'm not going to say anything about it. But I did mention this. This is an ADP. It's also called, by the way, control Lyapunov policy. That's the other name for ADP. So here it is, ADP, like that. Now the difference is this requires you to solve a QP in every step. Okay? So that's what this requires. And there's lots of ways to find a good one. In fact, yesterday I showed you one. And let's look at what happens in the quadratic case. In the quadratic case, the control law, you end up solving a QP. Every step. In my opinion, this is how systems with saturation should be controlled. Period. I think doing anything, this will beat anything else. There's no method that I know would come even close to this. Right? You put in all this nonsense with anti-wind-up and all this kind of crap. This is the right way to do it. And here are some numbers. These are actually out of date, but it doesn't matter because the numbers are good enough. So these are some systems here. Let's take here's a system with 50 states. That's probably bigger than you would ever control. It's probably bigger. 50 states, 15 inputs, 30 inequalities, and I think the inequalities are just limits on the input. I'm sure because that's twice that. So, and let's see. How long does it take to solve that? Again, that's also out of date, but it doesn't matter. That's 85 microseconds. Okay? And I don't give you the CBX times here. They're typically 1,000 to 10,000 times slower. Okay? So I think these numbers change everything. Right? Everything changes. All of control has to be rethought. I think not super high frequency control, but anything that operates at hertz, kilohertz, you have to rethink it. You may not want to do this. If it doesn't give enough improvement, don't use it. It's too complicated. That's fine. Those are all valid reasons not to use it. But you should be, I think this changes everything. Okay. So last time I talked about, yesterday I talked about parser solvers actually. So I'll go over that very quickly. And in fact, I think you've already seen most of this. But the idea is you write a problem in a natural form. And then what happens is if you follow rules which come directly from convex analysis, so very simple. If you follow these rules, then it's easy to parse a problem like that, transform to standard form and solve, right? And you get a huge gain in productivity. And then these are implemented using object-oriented methods. The earlier versions were done using compilers, like YAC, Bison. Okay, so CBX, I think you already saw this. In fact, I think it's even the same. I think it may even be the same example. So this would be the problem. It's not the same example. It's different. It doesn't matter. So you wanted to solve this, and this would be the CBX for it. And the point is, it's completely transparent, right? That it's obvious what it is. And so when CBX processes that, it, in this case, generates an SOCP, which you never see, and then it solves it, right? Okay, so now we're going to get to code generation. So this is kind of the newer stuff. So code generation, the first thing to do is there has to be a discussion about the big difference between general versus embedded solvers, because they're completely different. And in fact, everything you've used has been a general purpose solver. So a general solver, let's say for quadratic programming, why not? So it's basically this. When you use a QP solver, what it does is it handles a single problem instance with any dimension or sparsity pattern. If you have a QP solver and you call it to solve a QP, it doesn't matter what dimension it is or what the sparsity pattern is. It should just work for QPs. It should exploit sparsity, but it doesn't. It should just work. It might be slower, it might be faster on some instances, depending on the sparsity pattern, but that's fine. Now, these solvers are optimized for large problems because the complaints people who write solvers get are things like, hey, my problem only has 3,000 variables and it's taking 25 minutes. What's going on here? These are the complaints you get. Okay? So you optimize for large problems. You don't care about small problems because if it executes faster than 1 second, the general rule of thumb is who cares if it's a little faster than a second. It has to deliver high accuracy. There's a very interesting reason for that, which allows me to make another comment. So let me ask you, I'll just tell you. Typically, a solver will deliver, if possible, 8 significant figures, 10 digits of accuracy. That's good. Okay. And you might ask why. Why do you need that? Is it because in applications you need 10 digits of accuracy? The answer is absolutely not. I'm not aware of any application that requires more than 2, maybe 3. In an extreme case. By the way, I'm assuming that the variables have been intelligently scaled. So once the variables are intelligently scaled, you do not need more than 3 digits of accuracy, period. And you think about it very carefully. You certainly don't need it in control. Absolutely not. You don't need it, I mean, you can think about all sorts of other applications. In finance, you don't need it because the models themselves aren't even accurate to 1 digit, right? The first digit, or as a friend of mine says, we're happy when we get the sign right. So you don't need, 8 digits of accuracy. I mean, there might be some cases where you do, but I'm suspicious if you go to anyone doing some real engineering or something like that, and they say, oh no, this has to run in doubles because it doesn't work in floats, something is wrong. Deeply wrong, and you should look into it. Or if it's a vehicle, don't get in it. Because it doesn't make any sense. That's not real engineering. If whether or not something works depends on the 8th or 9th significant figure, or for that matter, the 4th significant figure, that's not engineering. That's called, or it is engineering, it's called bad engineering. Right? So, alright, so back to this. The point is, the reason that when you write a general purpose solver, you have to deliver 10 digits of accuracy is because users are incompetent. That's why. When they solve a problem, some of their variables range between 0 and 10,000. Others range in the 0.001 range. You see what I'm saying? Why? Because some are in millivolts and some are in meters per second. Because one's a sensor signal and the other's some velocity, right? So, anyway, so what happens, it is convenient for the user, right, to not worry about it. But the point is that in a final production system, you'd never do that. You scale things correctly and so on. So that's why you have to deliver 8, 10 digits of accuracy, is to cover up user error, user incompetence. I shouldn't say incompetence. When you're doing rapid prototyping, it's nice to not worry about scaling, right? Are you looking at someone who recently scaled something? Oh, no, only 2 or 3. Okay. I can keep track. Actually, it was 2 things. Anyway, all right. So this is a general purpose solver. It was a big breakfast. Right. That's part of it. Okay, so now the embedded solver is very different from a general solver. An embedded solver is this. It's a completely different problem. Although it sounds like you're doing the same thing, like solve a quadratic program, it's different. An embedded solver, you solve many instances of the same problem family, but with different data, right? And the problems are small. And the idea is here, in an embedded solver, by that time you should have scaled things correctly, right? So you can deliver 3, 4 digits of accuracy, more than enough, right? But the other thing is you have to satisfy a hard real-time deadline. These things stop either when they get bored, when they hit a maximum iteration count, or when residuals are smaller than some number. So you get variable execution time, which is completely unacceptable in a real-time embedded system. These things have to have a hard deadline. Okay, so embedded solvers, how do you do this? Well, look, if a general solver works, use it, right? If you are doing a supply chain and you have some stupid CDX thing that does it, and that solves it in 3 seconds or something, and you make a decision every 10 minutes, yeah, go ahead, put it in there. Of course, you have to wrap all sorts of crap around it to make sure it actually works, right? Because one in 1,000 times it fails, right? Otherwise, you can develop custom code by hand, or automatically via code generation. And if you do this, you can exploit things like the sparsity pattern, data ranges, and at code development time. And so we've done stuff with interior point methods, but there's many other things. The shocking thing here is you typically get a speed up that's between 100 and 10,000 x. So had that number been 10x, I would not have been too surprised. But in fact, it's not 10x. It's 100x or 10,000x, right, depending on the object. Or 1,000x is typical. Okay, so how do you do this? Well, code generation will work like this. You specify a convex family in natural form via discipline convex programming. So you declare these, but you also declare a parameter. When you declare a parameter, it's basically saying this is a quantity which will only be known at solver call time. It's not known at code generation time. Right? One that's known at code generation time is a constant, of course. Right? So you do this. Then a code generator, offline, analyzes the problem structure, chooses the elimination ordering in the linear solvers, and then generates solver code. And the idea is you can spend a whole lot of time generating code and compiling it, by the way. I'll say something about that. But the idea is you'll save a lot of time when you solve problem instances. Right? So the difference between a parser solver and a code generator is this. In a parser solver like CDX, you take a problem instant, the parser parses it, solves it, transforms it back, and you get the answer. Okay? It's complete, but if you call it multiple times, like to make a trade-off curve or something, they're incredibly stupid. It parses it again. Like 1 second later, it parses the same problem again. The data has changed a little bit, it does it again, as if it never saw it before. A code generator looks like this. You describe the entire problem family. The code generator then generates source code, like flat C. Then you compile that into a custom solver. At which point you have an unbelievably fast function that maps problem instances into solutions. Right? So that's what, and this is of course completely, this is computer science from 1960. Right? So this is not exactly a new idea. Okay. So there's one that my group developed something, well several, but one is called CDXGen. It's just a proof of principle, proof of concept thing, but it actually works. It handles small problems that transform to QPs. And we focused on small problems. You can do it for large problems too, but we focused on small ones because we were so irritated that people in optimization don't even talk about things, small problems at the microsecond level, so we thought we would. And what it does is it generates flat C source, everything. It generates make files, flat C source, all of it. It generates documentation automatically. Because once you're doing this, you might as well, right? And in fact, what happens is this, what comes out, the C source that comes out has no libraries, 0. You have to link in the math library, but only if you want to turn on the diagnostics, and that's, you only need one thing, square root, to give the norm. That's it. Otherwise, it requires 0 libraries whatsoever. Okay? None. It's almost branch-free because the code that's generated is completely explicit. And what this means is, if you know about these things, it says that the compiler goes insane. It has a heyday. This is a compiler's dream, right? Because it's basically, it's completely explicit. It says, get that number, get this one, multiply them together, add it to this thing, and stick it there. So what it means, and there's no branches, almost no branches. And what that means is the compiler is free to rearrange the calculations any way it likes, in a way where it can be absolutely certain that the semantics is preserved. Okay? And the result is you would run something like GCC minus 03, right? And you take a baby little problem, and it could actually run for 2 minutes, right? That's the amount of time it takes to build some big, serious piece of software. And this is, you're building one tiny little function, right? And what comes out is unbelievably optimized. In fact, it was good news. We have no idea. We don't even know what it did, but you end up with things like 70% FPU utilization and things like that. So we're glad we don't have to worry about it. So how does this work? Again, if you know about these things, that's great. I believe everyone should know about it because if you do this kind of stuff, you should know about numerical linear algebra, and you should know how interior point methods work and things like that. But in fact, you end up solving an integer point method, a KKT system, every step. Well, about 10 times per solve. And part of that is making a factorization. We use a direct LDL transpose factorization. We use regularization integer refinement for, in fact, I would replace extreme with total. Because in fact, again, if you know about how these numerics things work, there's only one way a numerical code can fail. I mean, there's stupid programming errors, right? But numerically, there's only one way they can fail. It's in division. There's no other way to fail. Well, you can multiply two numbers and go out of range. If you're multiplying two numbers and they're going out of floating point range, that's an overflow, you're in big trouble anyway. So that's not, the real way to fail with reasonable data and stuff like that is to divide by 0. And in fact, you can arrange for this for the following. There are no calls to div. None. The only call is to sdiv, which is a safe divide. And the safe divide is this, because every time you divide in this problem, you know the sign of the denominator. And what happens is, if it's supposed to be positive, and you're supposed to divide by it, or let's say just take the inverse of it, right, of a number, if it could actually come out slightly negative. That's when you get screwed. That's when nothing will ever, because you had a number that's very small, you invert it, now it becomes very large and positive. But the problem is if the sign switched, it becomes very large and negative, and you'll never recover now, right? So in fact, all we do is, when a number is known ahead of time, which we determine at code generation time, we know the sign, then all you do is you replace it with the min of that and the max of that and some positive epsilon, and you divide by that. And what that means is completely safe. I should also add something about that. We went down and talked to the people who actually fly all the missions for NASA. They're the ones who, we talked to the guy who okays all the software that actually runs on these things. And then it's weird and stuff like that. And if you're sort of if you hang around control theorists, you would imagine that they would ask questions like this, can you prove this algorithm works? Can you prove this? Can you give me a bound on that? Right? That's what because all around you go to a conference, that's what you hear people saying. Right? Robust this, robust that, I can prove this. Right? That's what you hear. That's what we do. I do this forever. So it turns out that's completely irrelevant in practice. Nothing can be less relevant. Here's what they cared about. They cared about libraries, and they cared about things like compiling and static. They were very concerned, but the most was actually just floating point errors. So just floating point faults, right? So this, it turned out, is what they were really. Now, by the way, I'm not saying that being able to do robust control is a bad thing. I'm just saying let's keep it all in perspective, right? And in fact, it turns out what people were really worried about was not proving an algorithm works. It was actually making sure that when it's 30 million miles from you, there's not going to be a floating point error. So, okay. So here's an example of what CVXGen looks like. The user would input something that looks like this. Again, it is like CVX. It is completely obvious what it does. And I don't even have to tell you what it is. It's self-documented. In fact, you can tell this is a problem from finance, and it's completely clear, right? One interesting thing here is the following. These are parameters. You don't have that in CVX. Now, what this means is these are quantities which are instantiated when you solve. That's what these are. And you need this declaration here, because that's needed by the parser to ensure that the resulting problem is convex. So this says, I don't know what lambda is, but I guarantee you it will be non-negative. Okay? If you don't do that, by the way, it will complain, because it will say this is not concave. If you remove this non-negative, it would say this is no good. Okay? So there's a kind of a sophisticated finance problem. And here are some examples. These are out of date. I'll say what the real numbers are. So these are just, I forget what scheduling is. Battery is some optimal charging of a battery in a hybrid vehicle or something. Suspension is an active suspension problem. It doesn't matter what it is. But these are problems with, a couple of hundred variables, a couple of hundred constraints. And then when you run these on CVX on a relatively powerful processor, they solve in things like a couple of seconds. By the way, that's quite impressive, right? You're solving problems with hundreds of variables, hundreds of constraints, and you do it around in a few seconds. That's actually pretty cool. But these things, typically we get a fairly big speed up. You might want to know the numbers here, right? So you go from 2 seconds to 110 microseconds, and these are out of date. That's actually about a third of that now, or something. It's like 35 microseconds, right? So if this were a factor of 2 or 5 or 10 smaller, it would be fine. But they're not. They're a factor of 10,000 or 100, at least 100. By the way, you could do the following. Instead of running it on a high-end processor, you could do the following. You could run it on a processor. That's a 100-watt processor. That's a 2-watt processor. And so you could actually trade off the speed for power consumption. I mean, if you care. So, by the way, we have not succeeded in running this on an ARM yet, but we're going to. So, we're going to, or an FPGA. What? Yeah.
As I understand, Civic Scan is a program which runs on conventional machines, or it generates code but runs not in embedded.
It generates flat C.
So how it's C can be embedded in a microchip?
Well, there are. I mean, well, we are not proposing this, but there are, of course, C to hardware chains right now, right? You can go C to VHDL, and then from there go. I'm not proposing that. Before that, we haven't even run it on an actual embedded processor yet. I mean, look, for high-end things, embedded processors have power, right? So, but no, we haven't run it on an ARM yet. But you run it on an ARM by compiling it in C, and by compiling in C and targeting the ARM. We haven't done that yet. Same for FPGA. Is this your question, or?
Yes, because in ISL it's not an embedded system.
That's not an embedded system. That's right. Nor is that really, but I don't know. It's getting closer, right? Oh, sorry. We have run this on. We have run CVX Gen on an iPhone. Sorry, CVX Gen generated code. We've run on an iPhone and on Android phones, like some Samsung. So that we've done. So. But we haven't yet done it like an ARM. Actually, what we really want to do is do it in fixed point. Because then when we do it in fixed point, it'll target any. Right. So, but we're too lazy to do that because then you have to worry about scaling and stuff. But we're probably going to do it anyway. Okay. So I'll finish up. The conclusions are that you can solve convex problems at the millisecond or microsecond time scales. And oh, by the way, when I talk to people in optimization about it, they're hoping it's because it's some new innovative algorithm that we're using. It's the opposite. In fact, we don't use the fanciest new homogeneous primal dual embedding. We go back 20 years and we use the very simple one. Okay, so there are almost no algorithmic innovations. Right? We only very carefully choose which method we do and then how we implement it very carefully. Okay, so you can't use existing codes; they just don't work. But it's using existing algorithms, right? And they claim that there should be many applications. I have no idea what they are. They're obvious in control. I don't know what the others are. I've already said this yesterday. So and the idea is you can make code generation methods. They yield solvers that are extremely fast, even competitive with analytical methods, and you can embed them in real-time applications. So here we had a very sad story in my group. There was a student, and I worked with him to show that you could do MPC extremely fast, right? So he and I worked out all the equations for the interior point calculations. I did it by hand, all the Gillespie factorizations, everything by hand. It took a whole weekend, one day of just like sitting there, and then tons of bugs and stuff. He wrote everything in flat C, well not flat, C with L8 pack calls. And it took months to kind of get it all right and to have the algebra become correct and the C implementation become, and months later, and that would be maybe like cumulatively a week or two of my time and months of his time, it worked perfectly. And we were just to show people, look, you can solve these things super fast. So we did this. Anyway, then another student in the group did the code generator, And at first, this first version of it generated code for the problem this guy worked on, and it was twice as slow, so everyone was fine. But within a month, it was twice as fast. And then this launched this other graduate student into a deep depression. So I said, what's wrong? And he said, well, you and I worked on this, me very minimally, but no, but I really did. I mean, I did all the Gillespie, I worked out all the algebra and stuff like that, and he worked on it for months, and he said, and this stupid code generator that knows nothing just generated code twice as fast as mine. And I said, no, don't worry, it's good. You went first, so to show what was possible or something like that. I don't think it cheered him up, actually. But anyway, okay. So that's a good. I mean, you can find all sorts of stuff about this online, and there's other people doing this kind of stuff now. And I would even I would highly recommend, actually, to people here, if you have an interest in these things, if you are pretty snappy, if you know your way around computing. You know like a modern language and stuff like that. These things are much easier to do than they appear. See, you can implement something like CVX in a week. Easily, in an afternoon, you can get a rudimentary one running, if you know something like Python. Right? I mean, don't even start if it's in MATLAB. Don't even waste your time. If you know a real language, these things are much easier than you think. And so actually, I'd like to make a pitch that if you know a lot of math, I know everybody here does. If you add to that learning about these modern languages, that combination, you can do a lot of damage. You can be very effective. And you can write code. I mean, these things are not hard. This is not hard to do. I know everybody, it looks like it's hard. You look at CVX and say, oh, that must have taken years to do it. It didn't. Right? So you can do. So anyway, I'd like to recommend you can do this. And it'd be great to have more people working on these things. Okay. I'll quit here.
Quick question, please.
Yeah.
You spoke about tiny design intervals, but what about memory?
So actually, this is quite embarrassing. We generate completely explicit code. So in fact, the codes are actually very big. They're not that big, actually. They're not big. The program size is large.
The memory consumption for these programs.
Oh, the memory consumption is completely minimal. Right? It's literally it's the LDL factor. It's the L factor. So but the program size is large. The good news, the bad news is the program size is large, but that's just because of the style we generated explicit code. In fact, if you want, I'm here, so if we want and we get an acceptable internet connection, we can play with it if you like. But the program size is large, but in fact, there's almost no branching. So basically, it looks like here's the code, and you kind of go like this. So what happens is it's quite fast. Yeah.
Wanted to ask, you said not waste time on MATLAB and go with the Python. Just was curious, you mean only the speed or some other reasons?
No, other reasons. Other reasons. And I've said this also to a bunch of people in smaller groups or something like that. But around people who do real high-tech stuff. I mean, this is not totally true, so don't take it totally seriously. But MATLAB is not a real language. It's a joke. Right? And I mean, if you're in computer science, it's kind of a joke. It's like Excel or something. I mean, you go ahead and use it, that's fine. It's not a real language, right? It doesn't have a real object model, with inheritance and all this kind of stuff. So Python is a real language. In addition, Python is open source. So that means it's free and it works. These are the advantages of open source things, right? They're also designed by intelligent people in computer science. Right. So also it's universally used. Right. Python is used easily 1,000 times more than MATLAB. In our little group, the little people we hang out with, our little group of people, you go to ACC, CDC, everybody uses MATLAB. Well, we're a tiny little minority. The real stuff is done in things like Python, C++, Java, these things, Ruby. So and the other thing is, if you want to do anything other than like fiddling around with a couple of matrices, you can't do it in MATLAB. You can't walk a tree or something like this. I mean, it's a joke. And they have some toolboxes in MATLAB, but you want to do something real, like scrape some stuff off a website or something. In MATLAB, it's a joke, right? In Python, it's 10 lines. That's my reason.
When you speak about Python, do you mean Scilab package or some other packages?
No, Python is the base, and then there's all sorts of different packages you can import, right? If you want to have something that kind of looks like MATLAB, you can import one of those things, like Scilab or whatever it's called, SciPy or something. There's do convex optimization. There's CVX, what's it called, Opt by Lieven, Vandenberg, right? So there's lots of packages. And unfortunately, it hasn't really settled out as to which are the best.
Which of them you prefer?
Okay, so this is very embarrassing. But once you get to a certain age, you're not obligated to switch immediately. So I use MATLAB. I'm embarrassed, but all my students use they all use Python and Ruby. That's even the more advanced. And even beyond that is Scala.
But there are less applications for Ruby.
It's actually the exact opposite. For Python and Ruby, there are infinitely more packages of infinitely higher quality than for MATLAB. Right? Now, they're not the ones you expect, right? There's not a control toolbox for Ruby or something, or Python, right? But there are unbelievably sophisticated things for these. I mean, if you want to do anything, well, except solve an audio equation. So, anyway, I think the answer to that is you should write a control toolbox for Python called ControlPy, and then make it open source. That would be great. Actually, I'm serious. Yeah.
Can we supply this gen with analytically derived gradients?
No. In the current version, no. But I guess my claim is, it's not hard to do this. You could actually do this yourself, and then you could do that, something like that. So, then you could do it easily. You'd have to supply C source, right? C functions. But yes, you could do that. These things are not hard to do. You just have to get into it.
So yesterday you told us that the most prospective directions is like high dimensionality problems. I think you want some basic problems in optimization. And I want just to repeat the question I asked you last year in the other.
Yeah.
What Murari was there? His fast NPC.
Yeah.
And he told that probably with fast solvers is like a future of optimization. So I just want you to be honest to say that do we really have some space here to do some stuff, or you already did all?
No, we've done almost nothing. When you start using these, you realize they kind of don't work. CVXGen doesn't work, it takes very little to make it not work in terms of problem size, right? And it's for no good reasons, because we generate code completely explicitly, right? So I think there's tons of stuff still to do. Including, for example, this is just a point of a proof of concept thing. It does work. It's being used, but there's tons of stuff to do, I think, and improvements. So I hope I didn't give the impression otherwise.
And we still have future with our baby problems, right?
With what?
With our baby problems. I mean,
without what?
Baby problems, low dimensionality problems. We still have future.
I think so. Actually, I think to me the really interesting part is this: we just wanted to show you can do this. Other people will do it better, for sure. That's coming. I hope. Maybe some of you will do it better. So, I mean, I'm not an expert exactly on numerical methods and things like that. I'm not. So, but we did it. So, if I can do it, then other people can do it. It's not that hard. So, I think the interesting part is not. I mean, someone should work on building better tools for these things. But I think the really interesting part is this. You go back and you rethink every application you know of, every method you know of, and you simply ask yourself, in this context, what does it mean that I can solve a quadratic program or a convex optimization problem in 50 microseconds? That's what you do. It could mean nothing, right? But I think right now the interesting thing is to search for applications. And that's wide open. Absolutely nothing's been done. Yeah.
Okay. Actually, when you want to meet the time constraints, does it mean that SDP optimization is out?
Sorry, what's that?
If you want to meet the time constraints,
Yes.
does it mean that SDP optimization is out?
No, absolutely not. No. In fact, no one's built an embedded SDP solver, but you could do it.
But you have no guarantee. I mean, you can be stuck
okay,
in
so
time.
that's a great question. Okay, so I'll answer it a bigger question, which is how in this stuff do you generate? How does CVX Gen actually give you an absolute upper bound on the time? Right? That's the question. Okay. Want to know how we do it?
Sorry?
Ready? It's very
I would
simple.
use the first order methods.
You would use, okay, no, first order methods would probably work unbelievably well. Someone should make, in fact, it would probably be easier to write a code generator for first order methods. So some of you should learn Python and write a code generator for first order methods. That would be great. In fact, honestly, it would probably work better than this, but okay. So you want to know how we guarantee that we stop?
In the SCC.
Yeah, you ready? It's a very sophisticated method, so you have to listen carefully. Right? It's for iter equals 1 to 10. Do a step. So we just do 10 steps, period, always. Okay? So we can absolutely bound the number of multiplies and adds we do. Just, you bound it.
But at each step you want to do some QR or something like what if you have the bad metrics you can be stuck in even in one step.
No, because we do all the factorizations are not, there's nothing iterative. We do iterative refinement, but we do one step. We do exactly one step of iterative refinement. We can count the exact number of operations. And in fact, in terms of time, the number of operations is much less important than the number of branches and things like that, and the number of cache misses. And so we do much more than simply bounding the number of multiplies and adds. We generate code that's almost branch-free, so there are no cache misses. Right? So, and then the real question is, what guarantees are there? Right? So if you stop in 10 steps, what are the guarantees? And the answer is none that are actually of the firm mathematical type, right? So in fact, what you do is we've tested these. In fact, I have another talk that goes into a lot of detail about this. But you test these very extensively. By the way, when you can solve a problem every 80 microseconds and you have like 4 or 8 cores on a machine, it means in an hour you can run a test of 1 billion. You can test 1 billion examples and things like that and get very good statistics on how these things work. We find that things like 10 steps and 20 steps are they're more than enough for any application. There's no application where that's not enough. And in fact, we even do things like, for fun, we run MPC, where we do 2 steps. And you haven't even achieved feasibility. So this would be completely insane to do. And guess what? You get excellent control. I'm not recommending this, but so anyway, so that's it. We just cut off the iteration. As to whether or not it's converged or not, as an empirical fact, I can say it has converged. If you wanted me to actually prove that, I cannot. What we can prove is there's no floating point divide errors. Did it answer your question?
Yeah.
Well, it answered it. You're disappointed with the response, but it answered it. Is that more accurate? Yeah.
Okay. No more questions. Okay. Actually, I have a question, but maybe I'll make a comment when we will listen to the next talk, which is absolutely different direction for solving optimization problems. Okay, then maybe we'll discuss.
Okay.
Okay, so thank you again.